Hello guys, you heard the term Big O through around in code reviews and in interviews. Today we'll make it concrete, not the math class version, the version that explains why your endpoint is fast today and on fire in 3 months. Let's get into it. You ship a feature. In testing it flies. 50 milliseconds. 2 months later the same endpoint take 30 seconds and your on-call phone is ringing. You didn't change a line of code. You just got more data. That gap between works on my machine and dies in the production is exactly what Big O predicts. And today we'll learn to spot it before it pages you. Here is the mental model to hold on to for the whole video. Big O is not a stopwatch. It does not tell you how many milliseconds something takes. That depends on your CPU, your database, the weather in the data center. Big O tells you something more useful. When your data gets 10 times bigger, does your work get 10 times bigger, stay flat, or blow up to 100 times bigger? Think of running a warehouse. The question isn't how fast is one worker. It's when order 10x. Does my workload 10x or does it explode? That shape. That's Big O. Segment 1. What the notation is actually measuring. The N you see everywhere is the size of your input. Rows in a list, records from the database, items in a request. Big O describes how the amount of work grows as that N grows. And here's the part that trips people up. We throw away constant. A loop does two passes over your data. O of 2n is the same shape as one pass, O of n. Both are straight line, one's just stepper. At scale, the shape is what kills you, not the constant. So, the trap to avoid. Don't spend a day shaving 10% of a loop, that's the wrong shape. If it's quadratic, a faster quadratic still time out. You have to change the shape, not the polish it. We'll come back to that later. Segment 2. The two you will meet every single day, and that's healthy. O of 1, constant time. The work does not depend on how much data you have. Looking up a key in a dictionary, grabbing an array element by index, checking a HashSet. One item in 1 million, same cost. The O of n, linear time. The work grows in a straight line with the data. One loop, one pass. Summing a list. Mapping orders to DTOs. Doubling the data doubles the work. Most heavily backend code lives right here. If your endpoint is O of 1 or O of n, you are usually fine. The danger starts when this innocent operation gets stuck. Segment 3, and this is the one that pages you at 2 am, O of n squared, quadratic time. The obvious version is a loop inside the loop, but the sneaky version, the one I see in real pull request, is this. A single for each over your orders. That's n, and inside it you call dot, contains on a list. The thing is, list that contains isn't free. It scans the entire list to find a match, so it is itself O of n times n in n squared. It looks like a clean 2-line blocks. It reads fine in reviews, and it is a time bomb. Let's make the pain concrete. With 100 items, n squared is a 10,000 operation. Instant. Nobody notices. With 10,000 times, it's 100 million. That's the jump from 50 milliseconds to 30 seconds. Your data grow 100 times. Your work grow 10,000 times. That's how it looks when it breaks. Latency that grows way faster than your data. An endpoint that's fine until your biggest customer logs in. And there's a database flavor of the exact same bug, the n+1 query. You load 100 orders with one query. Then loop and fire one more query per order to get it custom. Each query is fast, but you just made 101 round trips to the database instead of one. Same shape, same outcome. Segment 4. The good kind of scaling. The reason your database isn't dying right now. Of log n. Logarithmic. Each step throw away half the remaining work. Binary search is a sorted array, or an index lookup in your database. The beautiful part. Double your data and you add just one extra step. Go from 1,000 rows to a billion and you are adding maybe 20 steps total. Then of n log n. That's the price of a good sort. Order by under the hood. And it's why sorting a million rows is a non-event. The lesson for backend work. This is exactly what a database index by you. Without the index, finding a row is a full table scheme, O of n. With it, it's a log of n log up. Same query, completely different curve. Segment 5. How to read this off your own code in a review. By I. 2 rules. 1. Loops that run one after another add up. That's still linear. Still fine. And 2. Loops nested inside each other multiply. That's where n squared comes from. Then the thing to actively hunt for one line linear that secretly do n work. That contain, that any, that find on a list. Each one is a hidden loop. A database call inside of for each. That's an n plus 1. The fixes are usually small. Need fast lookup? Swap the list for a HashSet or a dictionary, and your O of n looks become O of 1. Querying in a loop, pull the data in one batch, query before the loop, computing the same thing every iteration, compute it once, and reuse it. You are not rewrite the app, you are fixing the shape. Let's actually what it breaks. Build a list of n numbers and a hash set from the same data. Now do a bunch of contains check again against each. At 1,000 items, both finish before you blink. This is why the bug hides in development. Crack n up to 1,000,000 and run it again. The hash set is still instant and the list crawls because every single contains is rescanning 1,000,000 elements. Wrap it in a stopwatch, or better, drop it into a benchmark.net, and you will see two completely different curves come out of a code that looks almost identical. That difference is big O, made visible. Put them all on one chart and the whole lesson lands in a glance. O of 1 is flat. Log n is nearly flat. It barely lifts off the floor. Linear is a steady diagonal, and log n rises a little faster but stay reasonable. And n squared, that's the one that turns and shoots straight up. Notice they all start in roughly the same place on the left. With small data, everything looks fine. It's only as I grow. On the right side of the chart that they fan out violently. That right side in production. The left side is in your laptop. Keep this table somewhere you will see it, from top to bottom. Best to worst. Constant and logarithmic, ideal. That's where lookups and indexed queries live. Linear and n-log. And totally normal. That's most of your code and your sorts. Quadratic, fine or small data. Dangerous the moment the data grows. And that's almost always a nested loop or a hidden contains. Exponential and worse. If you ever see that in a backend path, stop and rethink the approach. Quick recap. BigO is about how work grows with your input, not raw milliseconds. The order. flat to steep, constant log n, linear, n log n, then quadratic. Sequential loops add, nested loops multiply. The two killers you will meet most in real backend are a contains inside the loop and the n+1 query. And when something's low at scale, fix the shape, not the constant. Do that and you'll catch this in review before they ever reach in production. Thanks for listening to Code in Minutes. Don't forget to share, subscribe, and like. See you in the next one, guys. Bye bye.